class. Today we're transitioning to a new topic, which is the topic of isomorphisms. And it's a really key concept in the theory of groups, also one that I like a lot. So to set the stage, let me acknowledge that you've now spent a lot of time thinking about cyclic groups. And in particular, you've met at least two different cyclic groups with, for instance, 4 elements. On the one hand, you've met the group which I'll call G, that's Z4, the group that contains 0, 1, 2, and 3, where the operation is addition mod 4. And then on the other hand, maybe I'll call this group H, but it's U4, the group of 4th roots of unity. Its elements are 1, I, -1, and -I, where the operation is multiplication. And what I claim is that although at a glance these look like two very different groups, secretly they're kind of the same. And to see that, I think it's really helpful to look at the group table in both cases. So I've written out for you here on the left the group table for G under the operation of addition mod 4, and you can check my work there if you'd like. And on the right, I've written out for you the group table for the group H under the operation of multiplication. And again, you can check my work there if you'd like. And I've color-coded each of these tables for you to really try to highlight the similarity. So in the table on the left, I've drawn all of the 0s in red, the 1s in blue, the 2s in green, and the 3s in yellow. And in the table on the right, I've drawn all the 1s in red, the I's in blue, the -1s in green, and the -I's in yellow. And whoops, sorry, I just noticed there was a mistake in how I had written the table on the right. That should be corrected now. So the thing to highlight, now that I have it written correctly, is that the color pattern in these two tables is identical, meaning that if I were to take the table on the left and replace all the 0s with 1s, all the 1s with I's, all the 2s with -1s, and the 3s with -I's, the table on the left would just be transformed into the table on the right. And so the idea of isomorphism is the general idea that captures this sort of perfect similarity or matching between the group tables of two different groups. Here's now the precise definition of that term. So the setup to the definition is that G and H are two groups. And now I'll refer to an isomorphism from G to H. That'll be a function which I typically denote by the Greek letter phi from G to H, such that the following two things are true. Thing one is that phi is a bijection, and you've spent some time thinking about what bijections are in this course. That kind of means that phi is like a perfect matchup from the elements of G to the elements of H. And thing two is where the group theory comes in. I want it to be the case that phi of A star B is equal to phi of A star phi of B for any elements A and B in the domain G of phi. And let me highlight something that's a little bit weird about this equation, which is that on the left-hand side here, I'm combining two elements A and B in the group G. And so that star here, what is that? That's the operation in G. But on the right-hand side, I'm combining phi of A and phi of B, which are two elements in the group H. And so that star I have to interpret a little bit differently. That star I have to interpret as the operation in the group H. So in this way, somehow condition 2 here is giving me a condition that relates the operation in G to the operation in H. So to make that more concrete, let's look at some specific examples of isomorphisms. So first, let's look at the example that we started this video with, where G is the group Z4 under addition modulo 4, and H is the group U4 under the operation of multiplication. So my function phi from Z4 to U4 is going to be that sort of matchup between the two tables that we thought about on the first slide. Namely, phi is going to send 0 in Z4 to 1 in U4, it's going to send 1 in Z4 to I in U4. 2 in Z4, it sends to -1 in U4. And 3 in Z4, it sends to -I in U4. A succinct way to say all of this, by the way, is that it's described by the formula phi of k is equal to I raised to the kth power for any k from 0 to 3. So you can hopefully convince yourself that this really is a bijection. For example, you could draw a picture with dots and arrows, and there'd be 4 dots on the left and 4 dots on the right, and each one on the left would be sent to one on the right in a bijective way. But to know that it's an isomorphism, I need to know one more thing. So part 1 of the definition of being an isomorphism was that phi was a bijection. What was part 2? Part 2 says that if I take two elements A and B in the group G, and I combine them under the operation in G, which in this case is addition, and then I apply phi to it, well, there's some equation that says what's supposed to happen, but let's see what does actually happen in this case. So phi of A plus B, by this formula, can be expressed as I raised to the A plus B power. That's a consequence of this formula I've written down here. And then by rules of exponents, that's the same as I to the A times I to the B. But what's I to the A? That's the same thing as phi of A, again by that formula for phi. And I to the B, well, that's phi of B. And since multiplication is the operation in H, I've successfully shown that phi of A plus B is equal to phi of A times phi of B, which is the second condition in the definition of an isomorphism. So sure enough, phi is an isomorphism between these two groups. Let's take a look at one more example just to keep getting the hang of what these isomorphisms are all about. So for this example, let's let G be the symmetric group S3, and let's let H be the group D3, which we don't think about all that much in this class, but it's the group of symmetries of an equilateral triangle. I've drawn that equilateral triangle here for you in blue and picked a way to label its vertices just for convenience. So if I want to describe for you a function from G to H, I have to give you a rule that takes each of the elements of G, and those are the elements of S3, there's 6 of them, I've written them out in a row here, and I have to tell you a way to take each of them and assign to it an element of D3, meaning a symmetry of this equilateral triangle. And here's how I'll do that. I'm going to send E in S3 to I, the identity symmetry of the triangle. I'm going to send the permutation 1, 2 to the symmetry that I'm calling A, which is reflection across the diagonal line I've marked in my picture here. And similarly, so 1, 3 is sent to the reflection I'm calling B, 2, 3 is sent to the reflection I'm calling C, 1, 2, 3 is sent to R120, that's rotation counterclockwise by 120 degrees. And lastly, 1, 3, 2 will be sent to R240, which is counterclockwise rotation by 240 degrees. So this is a long-winded definition of a function between these two groups, and I claim that that function is an isomorphism. Why? First off, it is a bijection, and again, that's something that you can hopefully convince yourself of by drawing a picture, even just mentally, with dots and arrows. S3 has 6 elements, D3 has 6 elements, and I'm perfectly sending one on the left to one on the right. So it is a bijection, but what's condition 2? Condition 2 says that phi of A composed B should be equal to phi of A composed phi of B for any choice of A and B in the symmetric group S3. Notice that I have a composition on both sides of this equation, because on the left, composition is the operation in S3, but on the right, composition is also the operation in the group D3 of symmetries. So it's not so obvious, I don't think, that this condition 2 is true, but let me check it in maybe one example, one specific A and B. I'll have to flip to the next slide for that. For instance, if I take A to be the permutation 1, 2, and B to be the permutation 1, 3, then this is the equation that I want to know is true. So let's see whether it is true. So first, on the left-hand side, I can sort of work my way from inside to outside. So the first thing I'll do is I'm going to calculate the composition 1, 2 composed 1, 3 in the symmetric group S3. And if you calculate that composition, you should get 1, 3, 2. So the left-hand side is phi of 1, 3, 2. And if you flip back to the previous slide or look back in your notes, you'll see that we defined phi of 1, 3, 2 to be R240. Now let's look at the right-hand side of this equation. We defined phi of 1, 2 to be A, and we defined phi of 1, 3 to be B. So now those are two symmetries that I need to compose, and, well, maybe I'll let you work out the composition of those symmetries if you're interested, but what I claim you'll find is that when I compose those two symmetries of the equilateral triangle, I also get R240, the counterclockwise rotation, by 240 degrees. So I've gotten the same answer on both sides. So that's another example of an isomorphism. Lots more examples of this sort of thing to come. So for more practice, I'll see you in class.